Hey class, Mrs. Anderson here. I wanted to take some time to record the video for 1.1 line of best fit and correlation. So first let's start with some definitions. So a line of best fit is a line approximating the relationship between the data, and it's used to help us make predictions, and more specifically on a scatter plot. And within the line of best fit, we have the correlation coefficient. The correlation coefficient tells us how strong that relationship is between the two sets of data. A scatter plot is a set of plotted points that shows the relationship between two sets of data. We have three types of correlation. Positive correlation is as your x increases, y also increases. When two things are positively correlated, they're both increasing. For example, as your age increases, your height increases. So as one variable increases, the other also increases. Then you have negative correlation. As x increases, y decreases. For example, the miles that you drive in your car versus the gallons of gas that you have. So as the more miles you drive increases, the gallons of gas in your car decrease. So those are negatively correlated. And then relatively no correlation is there's no relationship between the two variables. Like there's no relationship between my age and the amount of gas in my car. I mean, you could make an argument for that if you're young. Maybe you can't afford to put gas. But in general, there's no correlation between those two things. So what is the line of best fit used for? The line of best fit is used for approximating the relationship between two things, and it's mostly used for making predictions. So we want to make predictions. So approximating the relationship and making predictions. So in example 2, we have correlation. Correlation tells you the relationship between the two sets of data. So as in number 1, you can see as x is increasing, y is also increasing. That's positive correlation. Number 2, as x is increasing, y is decreasing. You can see the points are trending downwards. That's negative correlation. That's an example of what negative correlation might look like on a scatter plot. And in number 3, where all the data points are kind of spread out, you can't really see a pattern. That's no correlation. Okay, just a couple more vocab words. Now the correlation coefficient is represented by R and sometimes represented by just lowercase r. The correlation coefficient is given to us when we find the line of best fit, and it tells us the strength of the linear relationship and the direction of the line. The strongest, so it's a number between -1 and 1. When you have the correlation coefficient equal to 1, that's the strongest positive relationship that you can have. That means that if you have a scatter plot, all of those points are perfectly on that line. And then if you have an r equal to -1, that's a correlation coefficient of -1, that means all of your data points are on a line that has a slope that's negative. So it's like the perfect correlation, positive or negative. And then r equals 0 is no correlation. So it would look at like number 3 here. No correlation between the data. And then kind of in between that, so if we have a correlation of like 0.5, we could say that it is a moderatively strong correlation. Maybe about 50% of the data is being used, something like that. So the coefficient of determination, that's our variable that's given to us in our model, is r squared. Now the coefficient of determination is how well does the regression line represent the data. So how well can we rely on our model, and how certain can we be in making predictions? So that's the main thing. Like how well can we rely on it, and how certain can we be when making predictions? And that one goes from 0 to 1. And then these values between weak, moderate, and strong are some of the values that have been given. So 0 to 0.29 is a weak relationship. 0.3 to 0.69 is moderate. 0.7 to 0.9 is a strong relationship there. Okay, here's our first example. The data pairs give the number of U.S. births from 1990 to 1997, where X is the number of years since 1990 and Y is in thousands. So if X is the number of years since 1990, then at 1990, this is where X equals 0. So in 1991, that's 1 year since, 2 years, 3 years, 4, 5, 6, 7. So if our data gives us years, we need to convert that to X values relative to like our year 0. So we really don't ever want to use the years in our model. We want to find out what year 0 is and then represent those years based off of year 0. So here, year 0 is 1990. And then this is Y is in thousands. So this first Y is actually 4,158,000. So just to give you an idea of what that means, Y in thousands. We are going to use the values they gave us for Y though, instead of adding 3 zeros to it. So, all right, I'm going to show you this in Desmos. So I'm going to pull Desmos up here. So the first thing you need to do is create a table and then put these data values in the table. So at the top of the Desmos screen, top left corner, you see a plus sign. You hit that, you're going to pick a table. And then in the X column, you're going to put your X values, which were 0 to 7. So 0 and the blue key is enter. And then in the Y column, I'm going to put my number of U.S. births. So my first Y is this 4,158. It'll let me click in there. And then 4,111, 4,065, 4,000, 3,953, whoops, 3,900, 3,891, and 3,895. So I have my data in there. Now, if your Desmos has this little magnifying glass, you can hit that and it'll auto zoom in for you. But I found that not all versions of this app have it, or maybe it needs to be like updated. But the other way to change your window is to hit the little button up here that has the wrench on it, and you can change your X and Y axis. So our X values go from 0 to 7. So I might want to set my X axis from like -1 to 10 so that I can see all the points between 0 and 7. And then my Y axis, I want to go, my lowest Y value is 3,891. So maybe I want to start my Y value at 3,500. And then it goes all the way up to, let's see, the highest one is 4,158. So maybe I want to go to 4,200. And then that would be a way to set your window. So now you can see my scatter plot. So you can see that based on my picture, I have negative correlation here. The number of bursts is going down. So as the years increase, as X is increasing, the number of bursts, the Y is going down. So it's negative correlation. Now I want to find my line of best fit. So select another line here in Desmos. And to do this, we want to use these X1 and Y1 points. So we want to say that Y1, and we don't want to say is equal to, we want to do a line of best fit. So we want the approximation. So I go under the ABC button here and I want this tilde, this approximation. So that means Y1 is approximately equal to, and then I want to do M times X1 plus B. So I want a line of best fit, so MX plus B, and I want to use X1 and Y1 as my statistics. So get rid of that. So now you can see here, I was given the statistics, R squared, that's my coefficient of determination, and it's 0.94, so it's strong. That means that this model would be reliable to use to make predictions. And R equals -0.97. That means that the data and the line of best fit are strongly related. It has a strong relationship between the two, and it's a negative relationship. Then we don't have to worry about the residuals. Then the parameters, this gives me my M, and remember M stands for slope. So my slope of my line is negative 41.46, and my y-intercept, my B of my line is 4141.75. So I can use that to write my line of best fit. So my line of best fit will be y equals mx plus b, but I'm going to substitute in m and b for the values that I found over here. So it's going to be y equals, slope was negative 41.46x plus, and my b 4145.75. So this was negative out front. So this is my line of best fit. Now I can use that to make predictions. I want to estimate the number of births in the year 2000. Well, remember that X was your year and Y was your number of births in thousands. So really this is saying estimate the number of births, estimate Y given the year 2000 X. So it wants me to plug in an X and solve for Y. So X is the number of years since 1990. So 2000 is 10 years since 1990. So I'm going to plug in 10 here. So Y equals negative 41.46 times 10 plus 4145.75. So we can go back to decimals and use the calculator here. So negative 41.46 times 10 plus 4145.75. So I get 37. Oh, excuse me. 31.15. Or I could say that's approximately this in thousands. So that's approximately, I'm going to round down to 3,731,000 births in 2000. Okay, so the correlation coefficient, and what does it mean? So that was our R, the correlation coefficient, and that is our negative 0.9713. And what does that mean? Since it is very close to -1, it's going to be a strong negative relationship. What does the slope mean? So I'm going to get rid of this for a second. So the slope in this line was 41.46, and that's negative. Now we have to remember that the y values are going by thousands, and so slope is rise over run. So the rise here is your number of births. That's your y-axis. And then your x was in years. So this was going down negative 41,000, or we could even say negative 42,000, 41,000 and a half births per 1 year. So rise over run. So birth rate is going down by approximately 41,000 per year. What does the y-intercept mean? So the y-intercept, based off of our model, is b equals 4145.75. And that tells us that, sorry, just a second. So, I'm sorry, that tells us at year 0, so the y-intercept is always the starting value. So at year 0, essentially, or in 1990, this means that our model approximates the starting value or year 1990 as approximately 414, we'll round up, 1,000 births per year. So now our actual number of births in 1990 was 4,158,000. So that's the actual number. This Y-intercept that our line of best fit gives us, that's our approximate, that's the model's representation of their approximate value, but that's at your year 0. So if you're not given the beginning of the year, like sometimes you have to go backwards in a model and find where the beginning was, that would be the Y-intercept, where you would want to find the beginning. Okay, I think I'm going to go to this one because this is a good example. All right, so I am going to delete these and start over by, again, choosing a table. And then I'm going to put in my points, 0, 1 to 9. This time, it is number of years since 1989, but it's already given to me in years. Or in years since. And we got 57, 76, 107, 234, 371, 688, 678, 716, 894, and 918. Okay, so once you get your data in, then you do y sub 1 is approximately equal to mx sub 1 plus b. And that gives you your data that you need. So then your approximation line is y equals, and it's going to be mx plus b, where the parameters down here are your m. So m is 110.12x plus, oops, actually that's a negative, so it'll be minus 21.62. Okay. And the correlation coefficient, that's our R, so we need that, 0.9739. So I think we can move that aside for a minute. I think we're done with the calculator for a second. So first, this is a table that shows the enrollment for the National Youth Service Program from 1989 to 1998. So 1989 is our year 0, and 1998 is year 9. So the correlation coefficient being 9.9739, that means that there's a very strong correlation. Oh, and it's positive. I just realized that we never looked at the picture of the data, so we can go here and zoom it back in. So you can see that the line is very fitting to that set of data. So there's a strong positive correlation between that data, between the number of years and the enrollment. Okay. So if the pattern continued, how many people would have been enrolled in the 2010? So in 2010, how many years is that since 1989? So 2010, take away 1989, how many years is that? Should be 21 years, right? Yeah, 21 years. So I want to plug in 21 here. So we got 110.12 times 21 minus 21.62. Oops, I can't put the equals there. 2,290.9. So how many people would have enrolled in the city program in 2010? For sure 2,290, because 0.9 isn't quite a full person. So for sure 2,290 enrolled, maybe approximately 291. You know, there's almost enough to say one more is enrolled there in 2010. What is the meaning of the Y-intercept? So I wanted to do this problem to show you the Y-intercept of the model. So the Y-intercept in the model here is negative 21.62. Well, the Y-intercept represents our starting value, and the starting value of a negative number doesn't make sense when you're talking about enrollment. So this means that there is negative 21.62 enrolled in 1989. No, that doesn't, I mean, that is what it's saying, but this doesn't make sense. So here our model doesn't make sense for this situation. This is our model's approximation. Now the actual Y-intercept of our data, or the starting value of our data, was 57. 57 people were enrolled at year 0. But because our line here, if we zoom in at that section, our line is, you know, approximating this relationship. So our model is crossing up here at 57. Our data is crossing up here at 57, but the model is crossing below. So sometimes if we want a true Y-intercept, we have to go with our table instead of our model. Now, what is the meaning of the slope? I'm going to add that because that one's kind of hard to describe sometimes. The meaning of the slope in this time, the slope is 110.12. Now remember, it's rise over run. So along the Y-axis is our enrollments, the number of enrollment, and the x-axis is years. So 110 means that you're going up 110 and over 1. So it's 110 are enrolled per year. So you'd say approximately 110 enrolled per year. So really, when you're looking for slope, you're looking at the rate of change. How much is it changing? And when you're looking at Y-intercept, that's your starting value. So those are just to sum up how you would describe the rate of change and the starting value. Now you can find the examples that I skipped in the notes that are filled out, and I would recommend you trying that on your own if you need a little extra practice. Thanks for watching.